Today is our last lesson dealing with inverse functions, and you're going to need graph paper to do and continue with this lesson today. The first thing that I need you to do is build a table of values and a graph for the function f at x equals x squared. So remember, when you're building your own table of values, always have some negatives in the x column and some positive. You can choose whatever numbers you want. In class, we've often used -2, -1, 0, 1, 2. But you can choose 5, 10, 15, being sure that you have some negatives there as well. -10, -5, 0, 5, 10, whatever you want. When you're done creating that graph and graphing it, on the same grid, do your inverse function of that graph. So be sure you create your equation first, if you'd like, and then substitute in and graph it. Or remember that you can always just switch your input and output values on your table of values and graph those. So I'd like you to pause the video here and do those two graphs, and then come on back to this clip. Now that you've created those two graphs on graph paper, answer this question under it. Are these graphs both functions? Why or why not? Now that you are done all of that, have a look at what I've done here. I have my basic graph. The table of values there shows that, -2 and 4, -1 and 1, 0, 0, 1, 1, 2, 4. And then I took the inverse of those, which means I just switched the x and y places, and I graphed them. And this is what the graph should look like. So your original graph here, and we know from other lessons, our original graph here is a function. Reason being that for every input, it only has one output. It passes the straight line test. Remember that if we drew straight lines through the graph, it would only touch it once. So just looking at the yellow graph there. So our original graph is a function. All parabolas are. Now our second graph, our inverse of it, does not pass our straight line test. If I go like this, down the inverse graph, it hits on that graph twice. You can see it touches there and there. As soon as a straight line touches a graph twice, it's no longer a function. That means there's two y values for each x. So here at the x value of 1, when x is 1, y is +1, but it can also be there at the -1. So our values, there's two outputs for every input. So that fails, so that's not a function. So it's really important to realize that when we take the inverse of a quadratic, it no longer is a function. When we have our graph here, if we look at the right side of the graph, just these values here, when I inverse this side of the graph here, it matched up. All of its values was this line here on our inverse graph. All of our ordered pairs here, for our left side, when we switched them, when we took the inverse, they all matched up down here. So the reason we want to take note of that is we can put some restrictions on our domain so that when we take the inverse of it, it is a function. So if I told you that none of your x values that you chose this time could be less than 0, meaning I want you to keep only your positive values. Now if that was the case, you would no longer have this side of the graph. This line would no longer be there. So when you took the inverse of that graph now, you're only inversing the yellow because I didn't let you use any positive values. So this line no longer is there. So therefore we only have our original graph, f at x, being yellow, and our inverse graph being yellow. And you can see now that if we only had half of the graph, then it would be a function. So in order to have a function, when you do your original graph, you would need to state all of your x values need to be greater than or equal to 0. Our range as well, y here is greater than 0. So if we put some restrictions on our domain, then we can keep our inverse as a function. All right, let's try one last example here where you're going to want to pause so that you can do the graph yourself and then come back to the video. So what I'd like you to do is graph the function f at x equals 5, x plus 1 to the power of 2 minus 3. Keep in mind that you can do this by table of values, but now that we've done so much transformations, we know it's faster and a more efficient way of doing it. So when you do that graph, that's probably the best way. Once you have your function graph there, take the inverse of it, graph it on the same grid, and then answer the questions below. Is the inverse a function? If you're saying that it's not a function, is there a restriction you can do to the original equation, the original function, so that it is when you take the inverse of it? So pause here, do that work, and then come on back to the video for the end of it. Now that you have completed your work, hopefully this is what your graph looks like. At the beginning, you may have had, let's put the bottom of this, at the beginning you may have had the rest of this graph here. You may have had the rest of your parabola going like this, and then you realized that this was not a function. So if you put restrictions on your original graph, let's get rid of this now. So if you put restrictions on the original graph so that you only allowed for this side to be graphed, what you would have to do in your table of values is say that you don't want to use any x values bigger than smaller than x equals negative 1. That way all of your graph will continue just on the right side. So as long as I state these restrictions here, then I'm going to have a function when I take the inverse. I'm only going to have the one line of it. Sorry, let's clean that up. When you take the inverse, if you only use values of x bigger than negative 1 on your original function, you're going to be left with half a parabola, which will then test positive for a function. We'll continue this discussion and activities in class tomorrow.